Hello, everybody. It's great to be here. So if running a marathon taught me something, it's endurance. And endurance is also necessary if you build any feature. So from the conceptual, from the idea, to actually shipping it and getting it out over the line to the customer, need a lot of endurance. And we are very close with collaborative editing. And I'm really happy to talk about the topic today. So there's a lot of people here. Just want to get sure in the right track. This is developer track. So is there any PMs here? Product managers? Just, okay, yeah, Sharif, of course. Doesn't count. Okay, want to get sure that you're on the right track. It's 2 PM-ish topics on the agenda. We'll go over them in, say, 5 minutes. The rest is algorithms, microservices, infrastructure, and security. So something I learned at Atlassian is, to look at why do we build things. The reason why we build things is very crucial because it helps you. It's a guide for decision-making along the way. And for Atlassian, we had a lot of requests where our customers were asking for, give us collaborative editing. Over 400 votes, which is really high for Confluence, one of the most requested feature. And it attracted our attention and said, OK, let's have a look at that. What does that mean? And we wanted to understand, so why do you want collaborative editing? What's the reason behind it? And we asked our customers and asked, so why do you want that? One of the things came up is that people, when they start working with Confluence, and there's already, it's hard to click on the edit button and change content, right? So that already, it's kind of an obstacle they have to go through, new users. Especially when they then hit edit and get a message, a warning. Attention, there's somebody else editing this content. It scares them away. So it prevents adoption. Now, if they accept that warning and say, OK, let's do this scary thing and edit this page, they want to save it back. Whoa, conflict, merge conflict. So this is really, it scares people away, these warnings, merge conflict, red messages. It prevents adoption. It's not what we want. We want to have adoption across the company with Confluence, right? Another reason is that customers were telling us that we have more and more remote teams, so we want to work on the same content. And if you have a conference, and then we can't actually really see what the other people is doing, it's just hard. So we can't really do it. We want to do it. And what happens is that they go to another tool, collaborate there, copy-paste the content, copy-paste it back to Confluence to have it in their main repository. So this is the reason why we did collaborative editing. Now let's have a look at what it actually looked like in the product. Yeah, that's the sad thing. It's a huge effort behind the scenes, but all you really get is this tiny little flag. And it indicates that, hey, there's this other person, and if this other person is doing something, it will happen here, right? So it gives you an indication where changes will happen if they do something. And it also shows you these are the other people on this document, so you kind of know, OK, I know these faces. Yeah, they are my mates. I can do it. Or this is my boss. Oh, maybe later. And then when you start working, right, you just see it. You see the other changes, how they come up in the document. And, you're not scared away. So it's trust. It actually, it changes from being scared to having fun. And so one of the first things that people do is they just try to delete each other's words and make a laugh and have fun. And that's the very first thing, which is, kind of good. It's good that we smile and have fun. But there's also another thing happening. It's this kind of, let's get things done. Let's get together in this room, sit side by side, work in this document, let's finish it off, and then we are done, right? Half an hour, and you actually get things done. One of our colleagues actually said this quote to us, and turkey in a bathtub. I was like, what, really? And he said, yeah, seriously, a turkey in a bathtub. It was the best thing we ever had, so it should be a prize. I said, OK, I don't know what you did, but it's good that you like it. So here we're already at the end of the PM-ish introduction, why we did it and what we did. And I want to dig a little bit deeper to talk about the technology. So this is the Confluence editor. And technically, it's an iframe with a toolbar on top of it. And in this iframe, we have some content, right? And the content is HTML, very roughly spoken. In that case, I bring up an example content. It's a body. And then we have paragraph with characters 1 and 2. What we do with this content is basically, on the client side, we read it, and we transform it into a virtual document that's represented in JSON, JavaScript, and it looks a little bit like this. So again, we have like a wrapper object, paragraph with some text, and that's the representation of the DOM in our data model. We implemented the technology in Lisp, actually. So we used Clojure to implement Synchrony, because it comes with a very good advantage. We can compile the code to JavaScript, execute it on the client, but we can also compile it to Java. It runs on the JVM, so we have on the server side and on the client side the exact same algorithms that we can execute. These algorithms are, kind of challenging, and so you really need to have the exact same execution in order to get it working. So this is what the content would look like. The tree is kind of the wrapping tree structure, and the P is the first child, and it has another child with 1 and 2, which would be the representation. So future code will only be Lisp, so we're only going to talk about Lisp. Now let's have a look at 2 users. So 2 users have 2 documents. In that case, Vito, he's a member of my team. Vito has this empty document. I have an empty document. And then Vito changes the document, inserts a paragraph with the content 1 and 2, right? So the first step we do on his client side is we translate it into this document. That's it. And then we try to find out the difference between the initial state and the state he's now at that moment, right? So this could be a copy-paste from somewhere. What we do is we walk through the 3 data structures simultaneously and compare them and create this delta. Delta is a little bit different from a diff. So it's not really a tree diff. It's this tree diff kind of walkthrough. It creates operations. It's a set of operations that basically, when you apply these operations on the initial state, you would achieve the resulting state. So let me quickly walk through these operations. The first element is a retain. So we retain the core, the root structure. Second is insert the paragraph, and within the paragraph, we insert the text 1, 2. So if I apply this delta on this tree, I would end with my state, the state I want to have. Now in Synchrony now, we send this delta to the other user who is connected to this document at the moment, and we just apply this delta, and the user gets the exact same state. So that's successfully synchronized one change from one user to another user. It's as simple as that. Now, let's look at another case. It's the concurrent case. So both users open the document, both users change something. So in that case, Vito is inserting 1, and I inserted 2 at the very same time. Now, the operation that I would have generated from the state empty to this new state would be insert 1 on Vito's side and insert 2 on my side. If we now would just do the exact same thing, change the delta, like move the delta from one user to the other, we would get this. And that would result in, if we apply it to each other's states, that Vito is here. Vito would get 3, 2, 1. Why? Because the retain refers to the tree. The next operation is insert 2, and the rest of the data is retained. So that's the result. On this side, we retain the tree, insert 1, and retain the 2. Now, this document diverged. It's not going to working. So what we have to do is basically to transform each operation to the local operation that happened before I got this operation, right? And in order to do that, we use operational transforms. Operational transforms is the same algorithm that Google Docs is basically using behind his scenes. It's just that we apply it differently on 3 data structures, while Google is just applying on linear structures. So what operational transform does, it's a very, very old algorithm, by the way, right? The algorithm is 40 years old. They used it for mainframes, basically, linear data structures. And what it says that if you have 2 operations, like A and B, you can transform this operation against each other, and the result would be A dash and B dash, where B dash applied to A equals A dash applied to B. Does that make sense? So if you look at this figure, the state 0 is on top, then we make a change A, and we apply B dash. The result is this new state at the bottom. The same on the other side, we have a change B, apply transformed A, and get this. So in case you're still awake, I need your attention. A very simple example. Say we have a delete at position 5 from a linear text, -1. Position 5, delete 1 character, right? And we have insert at position 7. Now we have to transform insert position 7 against this delete. The transformation would be then insert position 6, because at position 5 we deleted the character. And that's exactly what's happening with these transform algorithms. And what we want to look at is how would that apply to our case? In our case, we would transform it to each other. And this is, by the way, this code would work in Synchrony. So Synchrony, Lisp has a REPL. You could just drop this code and it would work. So let's have a look at what this transformation does. And on this side, that would be basically transformed the insert 2. And it would retain the 3, retain the 1, and insert 2, what we're getting from over there. On this side, we would retain the 3, insert 1, and retain the 2. Why? Why do we know that we have to insert 1 here, and here retain the first element? Well, in case of a conflict, the operational transform algorithm says, resolve the conflict with maintaining the user's intention. It's not really clear how you can resolve a conflict. So in some cases, like this one, we would just use the lexical order, right? So we can't know whether you want to have the 1 before or the 2 before. We don't know it. And it doesn't really matter, because the other user doesn't know it either, right? So we just use some deterministic logic to solve this conflict. And we just take the logical order, which works perfectly. Another case would be bold and italic. That case makes much more sense, right? So technically, it is a difference whether you wrap the bold in the italic or vice versa, right? For the user, it doesn't matter. There's a word which is bold and italic, no matter whether the italic comes first or the bold comes first. So we can just, make a decision and say, okay, whenever we have this conflict, the italic is the inner wrapper, the bold is the outer wrapper, and for the user, that is all right, and the document converges. So this is basically how we solve this conflict. If we apply these changes, here we would get 312, here we would get 312, and we are totally happy. So this is the core algorithms behind Synchrony, explained in a very, very simple example. Now let's look a little bit on the infrastructure that we implemented Synchrony. So in the cloud world, right? So it makes a lot of sense to move services with its own purpose on its own microservice. And that's what we did with Synchrony. So Synchrony is basically its own service, having its own cluster node, and there's only one service for all cloud. Doesn't mean that we can't deploy it to data center or server. It's running on the JVM, and it will be merged with server and data center, but for the cloud deployment, this is what we do. So we have a Confluence instance, which is, just sending the document to the two users. These two users make a connection with the Synchrony service. And then Synchrony service knows, OK, good, we have two users connected to the same document. What would happen now is that one user is changing something. We would basically compute the delta of that user. We would send it to the server, and then we would persist it in the event log. This is an event log. It's the database. Why an event log? An event log comes with the advantages that we don't modify data. Every operation that's coming in, it's just added to that store. That's crucial for us because we're going to get a lot of data, and we want to have a very, very low latency. So if an insert operation would take too long, that would be a big problem for us. And databases work very, very well if you only do inserts and reads, because they don't have to rebuild the index, the tree, to access the data. The moment you do updates or deletes, it's a problem for the database. But just adding data is really, really fast. And that's what we make use of. And once the data is persisted, then we acknowledge to the sender, thank you, your data is stored. And that was it was the first principle when we implemented Synchrony. Never lose customer data. So only the moment we have persisted it in the database, this client releases this operation from its local queue, and we know stored. Whatever happens to this node, to this service, it's persisted. And once it's persisted, we also notify the other clients and say, hey, change happened. You have to update this client on your local document. That needs to happen very, very, very fast. That's the second principle, low latency. If a website takes more than a second to load, it's really bad. And that's only from a request to shipping HTML and some resources back. What we do here is we have to compute diff. It's a whole lot of complicated operations, especially if you think we have to do these operations on really, really large documents, 10 megabyte documents or things like that. And all this cycle needs to happen very, very fast because you want to see the characters happening at the very same time. You don't want to wait for it. Now let's have a look a little bit on this mysterious Synchrony service, how it's working behind the scenes. So for the cloud deployment on Amazon, we use the load balancer, the elastic load balancer of Amazon. And when a request is basically coming into this load balancer, the request is forwarded to one of these Synchrony instances, Synchrony nodes. These nodes, every Synchrony node consists of two components. One component is the router. Second component is the hub. The hub is basically where we process the document. And every document is loaded on one hub because we don't want to load and save back and forth to the database. In order to have this very low latency, we need to keep every document in memory to make the operations really, really fast going through this first process we have seen. So the message is coming in. It's running on a JVM. We use Vertex for the WebSockets and for Hazelcast, the cluster detection. And that's actually happening when a new node comes up because there's so many users connected And this hop, the limit of this hop is CPU. So when we reach a certain level of CPU, basically we automatically spin up another node here, and then this node is talking to Hazelcast and say to the other node, hey, here I am, I can help you now. If you're too busy, I take over some of the load. And now, say in our case, we still have a user connected, and he's talking to this hub, right? So what could easily happen is that this other user connects, and the ELB is just sending this user here. So we don't have control of that. And now this router kicks in. The router knows exactly the number of nodes that are available, and we are using consistent hash map algorithm to basically route the message to the right node. In that case, this node would know, because of the ID of the document, that the document is loaded on this hub and would route the message here. And consistent hash map algorithm is very, very good for distributed systems, because whenever a node spins up or goes down, you don't have to move documents around in the cluster, right? The documents would always stay in the same segment, and you don't have to move them. So this is why we use the consistent hash map algorithm. This is basically how Synchrony works. Now, for Atlassian, it's very important to treat customer data very well. So this is why the first principle was never lose data. But we also have to protect the data of our customers. And if we store everything in a single database, all of the data is stored in a database. And if for every reason anybody should ever get access to the data, that would be a big problem, right? So we have to protect this data really, really, really well. And this is how we do it. For Synchrony, since this is now a service, right? For Synchrony, every Confluence customer is kind of a customer to the microservice. And every customer has its own key. So on cloud, we basically generate this key when an instance spins up. We generate a 256-bit AES key that we use to encrypt the data for this specific customer. And that's stored in Confluence. Now, in order to transport this secret key to this service, we have to do some magic here, right? Because we don't want to expose this key to anybody through the pipeline, because then, encryption doesn't make sense if you just send the keys around. So how we do that is that Confluence first asks the Synchrony service for its public key. Synchrony sends the public key, then we use this public key to encrypt this key. We forward it through the browser and then to the Synchrony service through a JWT token. JWT, that's a system that doesn't encrypt anything, right? It's just signing, right? So if we get a JWT token from this Confluence instance, we just know that this data comes from this instance, but this data is accessible. But what's not accessible in this JWT token, it's the encrypted key that comes as payload of the JWT token to the service. Now, the service has a private key that can decrypt this key that it just got from the JWT token and basically use then this key to encrypt and decrypt the data from the database. So another thing that we do is we add some salt to this algorithm either. So not all documents are just stored, encrypted basically in the storage with this key from the customer, but there's some salt on each single document. So essentially, every document has its own key to encrypt the data. If you have a key to decrypt one document, you cannot decrypt any other document in this store. And this is how we protect the data from access of evil people. Now to wrap that up, this is what Synchrony is, right? So it's a data synchronization service that's integrated in Confluence in an editor. And it brings you collaborative real-time editing. The challenge in integration there is undo. Because how the editor works at the moment is, it makes snapshots, and when you want to go back, it just replaces the snapshots. In a collaborative world, changes come from everywhere. So if you undo that changes, you would undo the others as well. That's really weird. So we had to replace this undo algorithm with a selective undo. You only undo your own changes, right? So that's the integration there. And obviously, you get remote selection. It's very important for the interface, so you know where the others are. And history of the document. You get that for free when you use Synchrony. Now, this is the integration into Confluence. It turns out that real-time is a very big topic for a lot of other applications. People don't want to wait for data. They don't want to, ask the server, give me your data. That would be weird, right? In today's world, we are a push world, right? Data is pushed to us, right? If you look at where the big trends are going, a couple of years ago, we had to go to Google to look something up, to some blogs over there. It was a kind of, we searched for data, and then we got the result. Today, we go to Facebook, and Facebook pushes us everything to us. So we get the data pushed. We don't want to go and ask for data. And that's where this technology is very helpful. It's a real-time data synchronization engine. Whatever data you have, any tree-structured data, this service can push it in every direction to every connected client, and you can collaborate on this data. It's not only applicable to collaborative editing, but essentially to all kinds of services. If you go to Ship It Live, you will see that Peggy will make a pitch there about better retros. It's a system to, make collaborative retros. And they're using Synchrony in the backend to synchronizing all the data around it. Some of you may know Enzo.me. It's a video platform of Atlassian Labs. And they are using all kinds of collaborative features, collaborative file lists, collaborative notes, all kinds of collaborative functionalities, and it's all using Synchrony in the backend to store this data. The integration is very simple. In JavaScript, it's just one line of JavaScript, integrate the service, make a connection, and then you have all these features available. So if you think that this technology could be useful for you, especially in a collaborative Confluence world, people will be used to work together on documents. And if you have a plugin where it would make sense that people can collaborate, then we would really like to know that. We would like to know what you want to do to understand your business case and your use case around that. So if you have that, please contact me and get in touch with me. I would really like to understand what you would do with such a technology. And what you would get for free is performance, scalable storage, and a lot of other things that you might find useful. That's all on this side. Thank you very much.